Welcome, everyone. My name's Adrian. I'm a senior engineer in the Sigma org, Silicon Graphics and Media org at Microsoft. And I'm super excited to be here today to share with you some of the details of our brand new API for machine learning, DirectML. In this session, we'll be talking about what is DirectML and how it gives game developers the power to use machine learning in their games. Later on, I'll also be joined on stage by a couple of our partners to show off some cool demos that were developed in collaboration with Microsoft using DirectML. This is our agenda for today. Firstly, I'll be giving an introduction to DirectML, as well as a brief walkthrough through the API. And then Kevin will be on stage to show off his real-time super resolution demo, and as well as to share some best practices for using the API. Next, we'll be inviting our partners at Unity on stage to show off some of the cool demos that they're doing with Unity and DirectML. And then we'll have our final summary and Q&A. So before we delve really deeply into it, could I get a quick show of hands? Who here has done anything to do with machine learning in their games before? Whether you've trained a model, you've developed one, you've implemented ML in your game? OK, that's a pretty good number of people. Do we have any rendering or graphics devs with us here today? Yeah, about a fifth of the room. Any data scientists or AI researchers? A couple. All right. So before we get into the real details, I want to give a little bit of additional context, which will help to frame the work that we're doing at Microsoft around ML and DirectML in particular. Over the past several years, there's been a lot of effort, a lot of investment that's gone into figuring out how to effectively develop and train a machine learning model. And developing and training a model involves things like picking a design for your neural net, tuning your hyperparameters, finding appropriate data sets to train on, and then once you're actually training, you have to deal with generalization and overfitting and so on and so forth. And this is a super well-studied topic, and there are thousands and thousands of academic papers out there that'll teach you to effectively train and develop your model. But when you think about it, training is really only half the story, right? Once you have your trained model, you need to put it into production and put it into the real world to do what it was trained to do. And this part of machine learning, the part where you take your completed trained model and apply it to real world scenarios, is called inference. And so this is the question that we're here to answer for you today. Say you have a trained model. Either you've trained it in-house or you've gotten it off the shelf from someone else. How do you actually integrate that machine learning model into your game? And our answer to that is a brand new API called DirectML. It's a low-level API for machine learning inferencing, and it's the latest addition to the Microsoft DirectX family of APIs. DirectML gives you low-level access to the hardware and gives you the building blocks for higher-level abstractions for machine learning. And just as Direct3D is to graphics, DirectML is to machine learning. Since DirectML is a DirectX API, it's designed with game developers in mind. And it gives you control over as much of the hardware as possible while still maintaining a standardized hardware abstraction. DirectML is available today, as of today, for you to use in your games. It's in the Windows SDK, and broad rollout to consumer machines, Windows 10 machines, will be happening in the first half of 2019 via Windows Update. As I mentioned earlier, DirectML is a bare metal, high-performance API for inference. It's built on top of D3D12, so it has a similar interface, and gives you the same level of control of your hardware that you'd expect from a DirectX 12 API. DirectML is a nanocom, native C++ API, which means it's great for games and for game engines. Just like with D3D12, DirectML gives you the freedom to control things like resource lifetime and memory allocations, transition and UAV barriers, synchronization between CPU and GPU, binding of resources to the pipeline, and so on and so forth. And this level of control allows you, the developer, to write super highly optimized code using DirectML's low-level primitives. DirectML features seamless interop with D3D12. This means that DirectML takes D3D12 objects natively through its API, and when DirectML executes machine learning operators, it does so natively on top of D3D12 resources. The This has a lot of advantages. For example, say you had your game and it has a D3D12 renderer. You could use DirectML to run a machine learning algorithm directly on the output of your rendering pipeline without having to involve any CPU round trips just so you can re-upload the data into some other API. Instead, you can take the output of your rendering in your D3D12 resource, which you probably already have, run it directly through DirectML, and get your machine learning result at the end. And this minimizes overhead in the cases where you want to either mix machine learning with your rendering pipeline, or in the cases where you want to share resources between them, because if they're running on the same GPU, for example. One of the greatest strengths of DirectML is its broad hardware support. DirectML provides machine learning acceleration on any DX12 capable GPU, and some examples are listed there. For example, on NVIDIA, we support all GPUs that are of the Kepler architecture and above, which means that everything from the 7-year-old GTX 600 series all the way to the RTX 2080 Ti is supported for high-performance inferencing using DirectML. On AMD, we support all GCN first-gen cores and above, which I believe is the Radeon HD 7000 series and newer. Of course, all of AMD's latest offerings, including the RX 500 series and the RX Vega series, are also fully supported for high performance with DirectML. Even if you're running on integrated graphics, as many people do, DirectML still provides full hardware acceleration. And as usual, any DX12 capable GPU is supported, and on Intel that happens to be the Haswell chips and above. And Intel has over 200 million of these iGPUs out in the market, so there's a potential for a lot of untapped power out there. In addition to its broad hardware support, DML is intended to provide high-performance inference. As I mentioned before, one of the ways it does this is with seamless interop with D3D12, which minimizes overhead. Also, DirectML will take advantage of architecture-specific optimizations and make use of ML-specific instructions or machine learning-specific compute units if available. So just as an example, let's say you have your game, you use DirectML to implement your machine learning algorithm, and you take it and run it on an RTX 2080 Ti. DirectML will transparently detect that this card has tensor cores available, machine learning specific compute units, and will utilize those tensor cores to greatly accelerate your machine learning. But you can take your same game written using the same DirectML calls and run it on an AMD Vega. And DirectML will perform architecture specific optimizations ideal for that card, and so on and so forth. And this level of abstraction over hardware is one of the key advantages to DirectML. You can write once using DirectML and be sure that it runs well on all hardware. DirectML has an extensive list of machine learning operators that it supports. And what this means is that no matter what model you're implementing, you can be almost sure that that you can implement your model end-to-end using DirectML, even if it uses some bizarre and esoteric form of neural net, for example. DirectML's completeness in its operator support is sort of not only for convenience, even though that's important, it means that you can be sure that with your model implemented end-to-end with DirectML, you get the level of abstraction, conformance, and performance that you get from DirectML. Speaking of performance and conformance, DirectML is designed for not only high performance, but specifically real-time high performance. If you have a machine learning algorithm and it absolutely must run within a 16 millisecond time slice, and it has to do that consistently every single frame, DirectML is perfect for your use case. But of course, being fast isn't necessarily useful if you get the wrong answer, right? And in machine learning, numerical accuracy and stability are often required to produce correct results. And to this end, DirectML is intended to produce consistent, accurate, and importantly, deterministic results across all of the hardware and the operators that we support. And finally, because DirectML is an operating system level API, it provides a stable platform for you to build your game on. games built using DirectML today will, of course, as you would expect, continue to work well into the future, into future versions of Windows, even as new hardware appears, new ML-specific compute appears, and as the ecosystem evolves. So that was my spiel. Now we can get into how you actually use the API. As I said earlier, DirectML is going to be very familiar to anyone who's used D312 before because it has such a similar style and a similar interface to Direct3D12. And what DirectML does at its core is that it executes machine learning operators, sometimes variously called machine learning layers. And these can be things like convolution, like GEM, general matrix multiply, like ReLU activation, pooling, LSTM, that kind of thing. And at a high level, there are 3 stages that you need to go through to execute a DirectML operator end-to-end. Firstly, you need to go through your device setup, your resource creation, and the creation and compilation of your operators. And then you need to initialize your operators exactly once on the GPU. Once you've done all of that, you can execute your operators as many times as you want on the hardware. This is the entry point to our API. DirectML.h is our header. It's in the Windows SDK. Pound include it, and you'll get everything. Like I said, this looks a lot like D3D12. DML create device is the entry point to the API. You use it to create a DML device, which is essentially a stateless factory object, and its job is to create the other DirectML objects that you need to execute operators. You'll see that DML create device takes as its first parameter a D3D12 device. And what that means is that you can use the same D3D12 device that you use for rendering as you do for machine learning. So there's no need to create multiple devices to use machine learning. Just like D3D12, we also have a debug layer, which we highly recommend that you turn on during development because it makes debugging much easier. And you can turn that on by supplying DML create device flag debug to DML create device. Operators. So the core of what DirectML actually does, of course, is that it executes machine learning operators. And you create an operator by calling the IDML device create operator, which takes as its first parameter a DML operator desk. And the operator desk essentially tells DirectML what kind of operator you want, as well as what are the parameters for that operator. So for example, if you wanted convolution, you would supply DML convolution operator desk, and that desk contains all of the properties for that convolution. So for example, you would specify what data type is the convolution running on, what type of convolution do you want, what's the size of your filter kernel, and so on and so forth. Once you have your IDML operator, the next step is to compile it. And you can think of a compiled operator as being a GPU-efficient baked form of an operator. And you get one of those by calling compile operator on the device. And compile operator is a point which you can think of as that's the point at which we generate shaders, we will compile them, and we will create PSOs, and we'll set up all other GPU state necessary to efficiently execute this operator on the GPU. Because compile operator is the point at which we generate shaders, it takes as a parameter DML execution flags, where you can control things like the floating point precision in which we execute. Tensors. In machine learning, data is stored in tensors, which you can think of as being like a higher dimensional generalization of a vector or a matrix. A vector is one-dimensional, a matrix is two-dimensional, a tensor is n-dimensional. And in machine learning and in DirectML, most of the time you're going to be dealing with four-dimensional tensors. Sometimes, in some cases, you may need a fifth dimension, but most of the time 4 dimensions is enough. The DML tensor desk is supplied when you create the operator, and it describes the properties of the tensor, the data that will be laid out. For example, it specifies the data type, it specifies the memory layout, it specifies the dimensions, the sizes of the tensor in each dimension. But of course, the tensor desk only describes the properties of the tensor. It doesn't contain the data itself. The data that you actually want to run your machine learning on isn't supplied to DirectML until you bind your D312 resources. And speaking of binding, binding is how you actually supply tensor data to DirectML. It's kind of, if you're a rendering person, it's analogous to how you bind a texture to a pixel shader using a shader resource view. In DirectML, you bind a tensor to an operator using a binding table, and it's the exact same concept. You can think of the binding table as being like something that wraps a range of descriptors in a descriptor heap that you, the application developer, has provided to DirectML. DirectML doesn't create any of its own descriptor heaps. It doesn't deal with that in any way. Instead, it relies on the application to create descriptor heaps, to sub-allocate from them, and to supply them to DirectML. And one of the reasons for this is because it makes it easier to integrate into many engines, and because it minimizes overhead. On some hardware, for example, it's actually kind of expensive to constantly switch between different descriptor heaps. So it's a common technique in many game engines and many games to have a small number of really, really large descriptor heaps that you sub-allocate from each frame, often in a ring buffer fashion. And because DirectML takes your descriptor heap, your range of descriptors, it means that DirectML can fit into whatever descriptor allocation mechanism you use in your D3D12 game. And of course, by using your descriptor heap, it means that we can minimize calls to set descriptor heaps, which maximizes performance. The way you actually bind to DirectML is with methods called like bind inputs and bind outputs, which take as inputs your D3D12 resources, or more specifically, ranges of D3D12 resources. And you'll notice that the DML buffer binding struct, which is what you actually supply to bind inputs and bind outputs, has as a parameter a native ID3D12 resource pointer. Again, DirectML doesn't allocate its own resources. It doesn't create its own resources. It relies on you, the application developer, to supply these resources into DirectML, which means that there are no requirements, no restrictions that we put on these resources. It's pretty common, for example, to use a committed resource for these, but they could be placed resources or even tiled or reserved resources, and that's totally fine. It just depends on whatever is most optimal for the design of your game. I should mention that some operators also require what we call a temporary or persistent resource, and the cases in which we'd use that is, for example, if we're doing a huge multi-level reduction. We may need some intermediate data on the GPU, and that's when we would use the temporary resource, for example. You must always query DirectML using getBinding properties to ask us how many bytes we need for our temporary and persistent resources. You can never assume anything about it. And the reason for this is because DirectML can and does choose different algorithms for implementing these machine learning operators depending on what's most optimal for your hardware. So on your NVIDIA chip, we may pick one particular algorithm. On your AMD chip, we may pick a different one. And therefore, we may require different resource sizes for our temporary and persistent resources. And so you can never assume anything. You always have to query DirectML because these things can and do change across hardware and driver versions. Compiled operators, once you have them, you need to initialize them exactly once on the GPU prior to initialization. If you try to execute an operator without initializing it first, you deserve what you get, which is probably going to be garbage. The reason why there's a separation between creation and compilation of an operator and initialization of that operator is that initialization happens on the GPU. And if you're familiar with D3D12 or familiar with DirectX in general, it's similar to the difference between creating your texture 2D and actually filling it in with the resource data. Creating the texture, of course, happens on the CPU timeline, and filling it with the correct data happens on the GPU timeline. You initialize operators using the operator initializer object, and because it happens on the GPU, they need to be bound and dispatched using the honor command queue for it to actually execute. I want to call out one particular flag that you can set when you create your operator. Inside the tensor desk, you can set a DML tensor flag owned by DML. And the effect of this flag is that when you initialize your resource, when you initialize your operator, the resources that you bind for input, the tensor data is essentially, the ownership of that tensor data is transferred to DirectML. And the reason why you might do this, the reason why you might relinquish control of the lifetime of your data is because there are some cases in which DirectML can transform your inputs in order to have them execute more efficiently on the GPU. So for example, on a particular piece of hardware, it may be more efficient for us to add a few bytes of padding at the end of your rows, or it may be more efficient to transform it into a different memory layout, or to pre-process the data in some way in order to make it faster to execute. And the owned by DML flag gives DirectML the opportunity to do this because it's essentially giving ownership of the data to DirectML. And of course, because DirectML is processing the data in some way, it may cause some additional overhead at initialization, but that's usually an acceptable trade-off because you usually only initialize once, but you execute multiple times. Once you've done all of that, once you've created your operator, once you've initialized it and bound it for execution, you need to actually execute it. And for that, we have the DML command recorder, which is stateless, and it takes as input your D3D12 command list, your compiled operator, and your binding table, which tells us what resources to read from as input and what resources to write to as output. And the important thing here is that, again, DirectML does not create its own command list. It doesn't create its own command allocators. It doesn't create fences or synchronize or do anything complicated like that. It takes your D3D12 command list and inserts the machine learning workload into your command list. This is particularly important because it allows you to interleave machine learning work using DirectML and your regular D3D12 rendering work into the same command list. This is useful in cases where, for example, you could have a really huge model, and if you don't want to execute it all at once, you can use this capability to execute just individual layers spread out throughout your command list, or even across multiple frames. Another reason why this might be useful is if you analyze the rendering of your frame and you notice that there's some section that is not, where you don't have full occupancy in your compute cores, maybe you have some dispatch that happens to be very memory bandwidth bound. You can then use DirectML to insert some compute-heavy machine learning work to get some free performance, so to speak, because you're increasing the occupancy of your GPU. And the ability to interleave machine learning work with your regular D3D work is something that is sort of unique to what DirectML can do. Once you have your completed command list, you need to close it and execute it just like any other D3D12 command list, and you submit it for execution using execute command lists on the queue. DirectML supports either compute or default command queues. Either one will work just fine, but it's interesting to point out that some GPUs support asynchronous compute, so sometimes you may get additional performance if you use a command queue, a compute command queue that's separate from your rendering queue, because it may give you some additional parallelism. So in summary, DirectML's design is really similar to D3D12, and it's similar not only in its style and design, but also its level of abstraction. DirectML, just like D3D12, is intended to be really low level, but also really low overhead, which means that you don't pay for the things that you don't need or you don't use. But this does mean, as a consequence, that DirectML relies on the caller to correctly manage, well, not only correctly manage, but efficiently manage things like descriptor heaps and sub-allocation, the way you do resource bindings, your resource allocation and memory lifetimes, your execution order and scheduling and barriers, and of course the synchronization between CPU and GPU in case you need it. But what this gives you, what this level of control gives you, is enormous opportunities in the ability to optimize your machine learning workload, especially if you're mixing it with rendering or using the same GPU for both rendering and machine learning. So I want to hand over now to Kevin, who will show you DirectML in action with his super resolution sample. Thanks.
All right, we on here? All right, yeah, thanks, Adrian. Yeah, so my name is Kevin Cogger, and I'm an engineer in the Advanced Technology Group at Microsoft. What my team does is we help game developers to do their best work on our platforms. And that includes things like researching new techniques and technologies to help build expertise and develop best practices, and then ultimately share that with all of you developers. So I've been looking at DirectML since mid-last year, and I've been working on building out a sample that'll help demonstrate how to use the API. I'm actually fairly new to machine learning myself. I think I only really first started looking at it maybe a year and a half ago. I've done a lot of learning and reading and experimenting since then, and I'm definitely not an expert, but I do think I'm starting to get the hang of it. So the sample I created, the primary purpose of it is to provide sample code that I can share with everyone to demonstrate end-to-end how to use DirectML, as well as a number of best practices, which I'll be getting into shortly. In addition to this, I wanted to prove the feasibility of using DirectML for real-time inference. So I wanted to take a relatively heavyweight model, one that typically wouldn't run in real time, and see how far I could push the hardware with it. Now, everything I'm about to show, we will be shipping all the code for this. It'll be at the DirectML samples GitHub, which is on the screen. And we're hoping to ship this sample within the next 2 or 3 weeks, I think. So what this sample does is it implements a super resolution model, which means it can intelligently upscale an image. So it can go by 2 times in each dimension, which means you could take a 540p image to 1080p or a 1080p image to 4K, for example. This was based on a TensorFlow model that was not originally designed for real-time execution. So using a 540p to 1080p upsample on a NVIDIA 2080 Ti, which is a pretty powerful, modern consumer-grade graphics card, it could take about 55 milliseconds to do this, which means it would run at less than 20 frames per second. Using DirectML, I got that down to 15 milliseconds, which is almost a 4 times improvement, and it runs at greater than 60 frames per second. Now, I do want to point out that this particular model that I implemented, it isn't something I'd expect you to take and put into a game directly. You might be thinking 15 milliseconds is still a pretty huge chunk of your game frame, and that's true. This model was really about finding something that, 1, was easy to understand and would make sense in a sample, and 2, like I said, I wanted something heavy to just see how far I could push it. So this is something that normally wouldn't be able to run at anywhere near 60 frames per second, but we were able to get it down there. I also want to give a quick thanks to NVIDIA. They provided the original TensorFlow model I used, and they also provided some help with the implementation. All right, so I will switch over to the demo. All right, so what you're seeing here is a video captured from Forza Horizon 3. I want to make clear it is a video, this isn't live gameplay, but what we're doing is we're upscaling the video in real time from 540p, so it was captured at low resolution, to 1080p. Now it's currently using the neural network to do the upscale. I'm not quite sure how well it'll come across on the screen, but I'm going to switch back and forth between this upscale and kind of a traditional bilinear upscale, so you can see the difference. So there's bilinear. One place you can really see it is the speedometer at the lower right, and there's the neural network result. There's bilinear again, and the neural network. Now if I pause it, I can zoom in on some of the details so you can see this a bit better. So again, there's super resolution, and there's bilinear. So you can see that the neural network produces a much sharper looking result. Also go look at maybe these trees over here. You can also see when using the neural network to do this, like I said, it's still running at greater than 60 frames per second. All right. Here's just another quick side-by-side comparison. Again, you can see things like the text or the texture detail on that cliffside come through a lot sharper using the neural network to do the upscale. This is despite the fact that both of these have the exact same 540p image as input. So while I was developing this, it was my first time doing inference at this low of a level, so there was definitely a learning curve, but I found that DirectML was pretty easy to get up and going on, given that I had some existing D3D12 knowledge. I think knowing D3D12 does help. As Adrian described, it's essentially built on top of it, so knowing that is a good starting point, but once you do, it's pretty easy to fit into an existing render path. I did learn a number of best practices, though, that can make a big difference for performance, so I'm going to go into those next. So first of all, fast paths. So as Adrian mentioned, DirectML provides optimized compute shader implementations for many machine learning operators. However, a lot of GPUs do provide hardware-specific paths that can run faster for certain scenarios. If you've heard the term meta commands before, this is essentially the same thing. And if your hardware has machine learning specific cores in it, like NVIDIA's Tensor cores, this is how you'd access those. Now these are designed for certain common scenarios and use cases, which means, for example, a certain GPU might support a convolution operator with a 3x3 filter size, but not a different filter size. That means the design of your model can affect whether or not you're hitting the absolute fastest cases in your hardware. So one tip I would recommend for this is to profile your model even before you've trained it, if possible. You can implement a model in DirectML, you can run it, you can profile it, you'll be providing random weights and random input data. The output you get won't mean anything yet, but at this point you just want to see how fast it runs. That way, if you need to tweak your model to get faster performance, you can do that before you've spent the time training it. This is just a quick example of how you could look into doing that. This is a screenshot from Pix, which is Microsoft's performance investigation tool. And Pix provides a range of features for capturing GPU and CPU behavior. In this case, I've taken a CPU timing capture, and I'm just looking in the event list at where I'm actually invoking that operator to send the command to the GPU. If you see execute meta command, you know it's using a hardware-specific path. And if you see dispatch, then it's using a compute shader. So for example, if you believe that your certain hardware supports a fast path for a certain operator, but you're not seeing it call execute meta command, you might need to investigate what exactly the requirements are on that hardware. That could be something, like I said, like the convolution filter could require a certain filter size, or it could have to do with your data layout or format, which I'll be getting into shortly. Do keep in mind, though, that these fast paths are opportunistic. They're designed to support common scenarios. They're never going to work for every possible scenario you might need, so you shouldn't expect every operator in your model to always be able to use a meta command. All right, data precision. So in DirectML, the default data precision is FP32, or 32-bit floating point math. This is also the default for graphics, so you're probably familiar with this, just regular floats. DirectML also supports FP16, or 16-bit float precision. And this is less precise, but a big benefit of this is that you can run essentially the same model in half the memory. It turns out that a lot of machine learning models run essentially as well using 16-bit precision, so that's an option that you have there. Do keep in mind you may need to explicitly convert your data to FP16 if it originates in a different format. Now, the performance impact of doing this can vary. On NVIDIA Volta and later, and AMD Vega and later hardware, they can run significantly faster on FP16. For other hardware, it can vary depending on what you're doing. So that's another reason you always want to profile and make sure you're getting the gains you expect. This is also an area of ongoing research and development by the GPU makers, so you may see further improvements here in the future. Related to that is tensor layout. So as Adrian mentioned, tensors are essentially usually four-dimensional matrices. And when you store those in linear memory, you have to decide how you lay them out. The default in DirectML is what we call NCHW, which means the first dimension is batch size, then the channels, then the height, and then the width. You can think of this as a planar format if you're familiar with that from graphics. For a standard 3-channel RGB image, you'd lay it out with all of the R values first in memory, then the green, and then the blue. This is the default because it's usually the fastest option. But if you need to, you can change this using a strides parameter on your tensor description. Again, you may need to convert the data just depending on how it was originally laid out. And a reason for doing this is that on some hardware, notably NVIDIA Volta and Turing architectures, these actually run faster on a different layout, NHWC, if you're using FP16. And that one you can also see in the image there. It's essentially an interleaved layout where you would have the R, G, and B values for one pixel next to each other in memory, followed by the subsequent pixels. As always, of course, you do want to profile and make sure you're getting the gains you expect. This is also an area where GPU makers are continuing to do research, so you could see additional enhancements here in the future as well. So because DirectML is built on D3D12, it uses regular D3D12 resources, as Adrian went into. This means all of the regular D3D12 best practices apply, things like minimizing resource barriers and avoiding redundant state changes. One particular tip I'd offer, though, is if you have a model with, say, a long linear series of layers, you can reuse some of your intermediate resources. You might have two resources and essentially ping-pong your data back and forth between them. You'd use one as input to a layer, one as output, and then just swap the role for each layer in the chain. I implemented this in the sample, and I was actually able to cut the total memory usage in half by doing this. Just keep in mind that your resources need to be large enough for whatever the largest input or output is that they'll need to hold. When you bind these resources, you'll need to get the DML binding properties struct, which is you get from get binding properties, which Adrian also discussed. This tells you the things like how many descriptors you need to provide and whether it needs any of those persistent or temporary resources. Now, Adrian did go into this, but I really want to stress, you really can't make any assumptions here. I got burned a few times during sample development where I thought I knew, for example, how big of a persistent resource I needed, but then I ran on different hardware or I even just upgraded my driver and suddenly that changed on me. So always make sure you get these dynamically and provide what it requests. Finally is constant data. So in machine learning, you'll typically have some data that's not going to change after your model's been trained. Notably, these are your weights. When you do, you can provide those when you initialize the operator using that flag, DML tensor flag owned by DML. This means that, again, as Adrian described, DirectML can make its own copy of the data. This really can only be for data that will never change because you basically lose control of it after DirectML makes its copy. The benefit here, though, is it can provide those optimizations based on your hardware. These are hardware dependent, so not all hardware will find optimizations this way, but it will never slow down your execution, so I recommend doing this whenever you can, and you'll get the benefits on all the hardware that supports it. When you do, the data will be stored in a persistent resource, so you'll need to keep that around whenever you execute that operator. But you can get rid of your original resource with your own copy of the data after you've initialized the operator to get some memory back. So to sum this up, I believe that real-time machine learning inferencing is still a pretty new area, and I think the best practices are still being established. I think we'll continue to see advancements both on the software development side and on the hardware side. So that means that right now there are some hardware-specific knowledge that you might need for how you optimize. DirectML abstracts as much of this as possible, but the few cases you might still need to be aware of are mostly around data layout and format, as I talked about. This is also why it's always important to profile on whatever hardware you can to ensure that you're hitting the fastest cases. Now, because DirectML builds on D3D12, a lot of existing knowledge there will take you pretty far. However, it does bring a number of new concepts of its own, and to get started learning those, I'd recommend, again, taking a look at that sample, which should be shipping in the next few weeks. It demonstrates end-to-end how to use the API, as well as many of the best practices that I just discussed. And again, that'll be at the GitHub repo on the screen as soon as it ships. All right, thanks a lot, and now I'd like to welcome Vlad from Unity.
Hello, good afternoon. My name is Vlad. I'm a software engineer at the machine learning department at Unity. And I'm going to talk a little bit about the work I've been doing for the last couple of months with Microsoft and DirectML. OK, yeah. For the last couple of years, Unity has been working hard to harness machine learning in the aid of creativity for our customers. From the ML Agents toolkit that maybe some of you are familiar with, that allows game developers to train smart agents and embed them in their game, via content generations and other projects we're working on that we'll talk about at a later stage. We've been wanting to integrate machine learning models into the Unity engine. So supporting inference on the various platforms Unity supports, it's quite a difficult task. We would like to offer our customers the same experience they have with other technologies in Unity: develop once, run everywhere efficiently. In the past year, Microsoft and Unity has worked together to accelerate Unity machine learning inference for Windows platforms. Last GDC, we presented our work with WinML, leveraging the WinML library to run inference on Windows. Unfortunately, we've discovered that while using high-level inference libraries, it's easier to integrate with, but it presents a certain set of challenges. One important challenge is complicated data flow management. Since the entire network is executed as one batch, we have to kind of run the data CPU to GPU back and forth, which complicates stuff. And in addition, you don't have fine-grained control over the execution. So again, you execute the network as one bash, so you cannot, for example, split the network between different frames. And when your network is pretty large, it can be a challenge. So in order to address these challenges, we've developed the Unity Inference engine. It allows us to execute network graphs within Unity, giving us full control over the graph execution and the data locality. For example, we can feed textures directly from the GPU into the inference engine without passing through the CPU, thus saving a lot of time, a lot of compute time. And we can control which layers are executed at which stage, so we can split network execution between different frames. At the back end, we're providing optimized CPU implementation for small networks where you don't need to harness the GPU, and you can save the GPU for more complicated rendering tasks and just run the whole network on the CPU. And we have an efficient GPU implementation using Unity Compute Shaders. So Unity Compute Shaders are automatically cross-compiled into all the platforms that Unity supports, so we get good out-of-the-box performance on all of our platforms. But several platforms provide, or several hardware provide additional acceleration, like the meta commands that were mentioned earlier. So how can we tap into that? In the back end of our inference engine, we've developed the ability to plug in specific platform low-level libraries like DirectML in order to achieve better hardware acceleration on these platforms. So we've decided to utilize DirectML because it allows us to harness the hardware acceleration on Windows platforms while still maintaining the benefits I mentioned before, data locality and control over the execution. And we are in the process of integrating DirectML into our inference engine to allow Unity developers to take advantage of meta commands and other hardware acceleration available with DirectML. And of course, since we're utilizing the regular graphics pipeline, we're saving on GPU stalls, and we have full integration with the rendering pipeline. Now, before we jump towards the demo, let me give you a little bit of context. Who here is familiar with or heard about the ML Agents Toolkit? About half of the room. So I'll talk a little bit about that just to give you some context. The Unity Machine Learning Agents Toolkit is an open source Unity plugin that enables game developers to train agents with deep reinforcement learning to embed them in their games. We have a easy-to-use Python API that you can integrate with and either use our pre-supplied TensorFlow-based implementations of several training algorithms, or if you're a researcher or you have like your own algorithm, you can also integrate that into the toolkit. And these training engines can be used for various stuff. For example, like the most obvious thing is controlling NPC behavior. And actually, in October at Unite LA, we presented a game that used ML agents for part of the NPC control. So the movement of the characters was controlled with ML agents, and the attack-defense strategies were done with traditional AI. But apart from NPCs, you can also train agents to play the game, for example, for automatic testing, and other stuff that you can use more AI in your game. So let's look at a couple of examples. Let me switch to the demo machine. All right. So this guy is Papo. We named him after the algorithm used to train him, which is called PPO, Proximal Policy Optimization. He's an absolute unit of cuteness. We've managed to encode cuteness into a neural network. There is no animation involved. It's all physics-based. We essentially trained the model to apply physical torque to his limbs so that he can move towards the target. In this case, the target is the stick, which I can throw. Whoop. And then he'll run towards the stick, and sometimes he falls. All these like stumbles and falls are artifacts of the training. That's how he actually learned to walk. And once he gets the stick, then we switch the target from the stick to the player, and he runs back with the stick. And the inference is done with DirectML in the background. But of course, if one puppy is great, what's better? So here we have 50 of them trying to run towards the robot-y device with tasty bones. So the puppies are unaware of each other. We train them. It's the same model that was used in the previous game with only one puppy. That's why they're kind of cheating, and sometimes they're hitting each other because collision still works. Physics, nobody disabled physics, but they're unaware that there are other puppies in the world. They're kind of a little bit selfish in that sense. But luckily, if one of them falls, the others can kind of kick him and he'll get back on his feet and keep running. Yeah. And of course, in this case as well, inference is done with DirectML. So to finish off, I'd like to talk a little bit about my experience with DirectML. So I came into this project with zero experience in DirectX. I've developed machine learning products in the past, but I've never worked with graphics rendering, DirectX, or anything similar. It was relatively simple to use the DirectML API. The most complexity came from using DirectX, managing DirectX resources, descriptor heaps, and all this jazz. That was the main learning curve to get into DirectML. But the nice thing is that DirectML has full integration, like it was mentioned before by Adrian and Kevin, full integration with Direct3D12, so that we can, for example, reuse Direct3D12 textures we use in Unity. We can just directly feed them into the neural network without having to go through any process of converting the data, which is very nice. A couple of tips and tricks that I just discovered while working and debugging stuff late at night. Have a way to debug individual layers. It kind of sucks if you feed your data into the network and then you get zeros and nans and you're like, okay, something went wrong. But having a way to debug individual layers is very important. One thing I discovered is it's very important to feed the network in topological order, especially if you have several branches, because regular barriers will not defend you against problems if you feed the network in their own order. And the most important tip is master the strides. The strides are a very important tool that allows you to do complex things like dimension broadcasting or having weird layout of your data and stuff like that. So it's a very important tool to master. So what's next? We're planning to fully integrate DirectML with the Unity inference engine. Right now, we've only done part of this work, and it's still in progress. And of course, further optimize memory, execution, like fusing layers with activations or saving memory, like Kevin mentioned earlier, ping-ponging buffers so that we can save a memory, stuff like that. So this is in the future. Thank you.
That was an awesome demo, wasn't it? One thing I want to just quickly point out is that Vlad's demo just a second ago, that was actually running on an Intel integrated part, which again proves that DirectML can do high performance inference no matter what hardware you're running on. So in summary, DirectML is available today for you to use and to start building your games on top of. It'll roll out broadly to Windows 10 machines in the first half of 2019 as an update via Windows Update. But if you want to skip the wait, you can install the Windows Insider program build right now, install the latest Preview SDK, and from there you'll be able to use DirectML. Our samples are available on GitHub, including, well, it will include the super resolution demo that we showed today. I think the pull request to actually add that to the public repo is still pending, but it will be there soon enough. And of course, there's also a link to our docs. You can get our headers and libs in the Windows SDK, as I mentioned, and that should be everything that you need to get started. Since this is our first public release of DirectML, we're super interested to hear your feedback and what you think about the API. So if you have any comments or questions or feedback, you can send an email to askdirectml@microsoft.com, and we, the DirectML engineering team, will do our best to answer your questions. And if you're working on some awesome new ML feature for your game, also feel free to shoot us a mail, because we'd love to hear from you, to hear more about what you're working on and your experiences using DirectML, the DirectML API. I would also recommend that you stay tuned to the DirectX blog, because we have some more information coming, and the slides for this talk will also be posted up there.